Here is a quick and very important review for exam 2. And this is question number 1. A stone of mass 5 kg slides down a frictionless hill of slope 30 degrees from rest. Find the velocity of the stone after sliding down a distance of 7 meters. The diagram shows the forces acting on the object. The weight of the object mg acts vertically down, and this can be broken up into mg sine theta acting along the plane and mg cosine theta perpendicular to the plane. But I've not shown mg cosine theta because you don't really need it. Since there is no friction, the only important force is Fx, which is mg sine theta, and according to Newton's second law, that should be equal to mass times acceleration. From which, because the masses get cancelled, you get Ax is equal to 9.8 sine 30, which is g sine theta, right? 9.8 sine 30. And when you put in the number for sine 30, you get 0.5. So 9.8 times 0.5 is 4.9 meter per second squared. So now, since we have to find the velocity of the stone after sliding down a distance of 7 meters, we know that the initial velocity is 0 meter per second because it's at rest. It says from rest. The acceleration that we have calculated is 4.9 meter per second squared. The displacement is 7 meters, and we have to find the final velocity. Using the kinematics equation, Vf squared is equal to V naught squared plus 2a delta x. V naught is 0, so I have not written that term. And then you have 2 times 4.9 times 7, which gives 68.6. That is Vf squared. And so when you find the velocity, you got to take the square root of that, and you get it as 8.28 meter per second. So what's important in this question is to understand that since there is no friction, the only force acting down is mg sine theta. So that's the only force acting. This is question number 2, and I'm using the same question, but this time we're going to have to consider friction. So you see that a stone of mass 5 kilograms slides down the same hill of slope 30 degrees from rest. Find the velocity of the stone after sliding down a distance of 7 meters, which is exactly the same as before. But now the coefficient of kinetic friction is 0.4. Now we have to consider all the forces, and the forces are, first, the weight that acts vertically down, and then you have the normal force, Fn. And since we have the x-axis along the inclined plane and the y-axis perpendicular to it, we know that Fn is already along the y-axis. So we need to break mg into its components, which gives us mg sine theta along the plane and mg cosine theta perpendicular to the plane. And friction is always opposite to the motion, so now we have friction opposite to the motion. The object is sliding down, therefore friction is up. So now considering the forces along the y-axis, you have Fn acting up and you have mg cosine theta down, and so Fn minus mg cosine theta is equal to actually mass times acceleration, but the acceleration is 0, so the right hand side becomes 0. When you rearrange that, you get Fn is equal to mg cosine theta. Fn is the same as mg cosine theta. Is that clear? And friction is given by mu times Fn, which is mu times mg cosine theta, because Fn is mg cosine theta. Next, when we consider the forces along the x-axis, we have mg sine theta acting down, friction acting up. So the net force is mg sine theta minus friction is equal to mass times acceleration, which gives mg sine theta minus friction is actually this whole thing. So in place of friction, I've substituted mu mg cosine theta, which is equal to max. Now since mass is there in all the terms, you cancel that out. You substitute the values carefully. You see the mu there, g cosine 30 is equal to ax. When you do the calculations, you get ax is 1.5 meter per second squared. Since we know the acceleration, now we can apply kinematics and find out the final velocity. Again, you use the same equation as before. We know that the initial velocity is 0 because it starts from rest, and so you have 2 times the a that we got, which is 1.5 times 7, gives 21. Take the square root of 21, you get 4.58 meter per second. Here's question number 3. In this question, you see that the major difference is the stone, same mass, is sliding up this hill at 10 meter per second. It is sliding up the hill. So now the stone is like given an initial velocity and is sliding up. So it's going to stop after some time, or after sliding up a distance of 2 meters. And you have to find the velocity after a distance of 2 meters. So it's not actually stopping, but you have to find the velocity after it goes up by 2 meters. And the coefficient of kinetic friction is given. You see the difference in this diagram now? The weight always acts vertically down, no change there. Fn is perpendicular. You break mg into mg sine theta and mg cosine theta, no difference there. But notice that now friction is down. Why? Because friction is always opposite to the direction of motion. Isn't the object trying to go up? Yes, therefore friction is opposite. So that's the big difference here. Therefore, when you consider the forces along the y-axis, like before, you only have these two forces. So Fn is equal to mg cosine theta, and then friction is the same, mu times Fn. But when you consider the forces along the x-axis, you have minus mg sine theta minus F. So because you have both moving down, so that's why minus mg sine theta minus F is max. And now substitute for friction as mu mg cosine theta, which I've done here. And then the masses cancel out. That gives you the value of ax as negative 8.3 meter per second squared. Now the negative shows that the acceleration is opposite to the motion, or rather that it is slowing down, which makes sense. Once you get the acceleration, use the kinematics equation. Vf squared is v naught squared plus 2a delta x. V naught is 10 meter per second because you're giving it an initial velocity of 10 meter per second. That's another change. And then 2 times a times x. Do the calculation, you get 66.8, but you got to take the square root and you get 8.17 meter per second. And I hope that's clear. Now, here is another question. Here, a boy throws a rock at an angle of 30 degrees with a velocity of 20 meter per second from a tower of height 50 meter. How far does the rock travel horizontally before striking the ground below? So the rock is given a velocity of 20 meter per second at an angle of 30 degrees. And this is the tower of height 50 meter. You have to find out the distance delta x, because the question says, how far does the rock travel horizontally before striking the ground below? So the first thing is you got to resolve this into the horizontal component, which is 20 cosine 30, and the vertical, which is 20 sine 30. And then focus on the vertical component first. So that's why I've written vertical here. So the vertical velocity is the initial velocity now, which is 20 sine 30, which is 10 meter per second when you plug in the value of sine 30. And then a is negative 9.8 meter per second squared. Delta y is negative 50 meter because it's going down. It's negative 50 meter. And you got to find the time. Now the kinematic equation that you're going to use is delta y is v naught t plus 1/2 at squared, because that has all these 4 terms in it. And then substitute the values. Negative 50 is 10t minus 4.9. Because it's 1/2 times negative 9.8, and so I take half of 9.8, rather negative 9.8, which is negative 4.9 t squared. So when you rearrange that equation, you get this quadratic equation. Be careful with the signs. And this is A, this is B, and this is C, and use the quadratic formula to find the time. This is the quadratic formula, minus B plus or minus square root of B squared minus 4AC by 2A. Do you have to know this? Yes, absolutely. And so when you plug in the numbers carefully, you get this. It's B squared minus 4AC by 2 times A. And solving that gives you the time as 4.21 seconds. Once you get the time, we can find the horizontal displacement, remembering that the horizontal velocity never changes. Therefore, just multiply that with the time to get the horizontal displacement. Now in this question, I've made a small change in that the boy is throwing the rock horizontally. So there is no angle here. He's throwing it horizontally with that velocity of 20 meters per second from the same tower. And again, you have to find out how far the rock travels horizontally before striking the ground below. So the difference here is that you need not resolve it into horizontal vertical because it does not have a vertical component. Or in other words, the initial vertical velocity is 0. A is negative 9.8 meter per second squared, delta y is negative 50 meter. Once again, find the time. We use the same equation as before. It becomes easier now because this whole term becomes 0. Why? Because V0 is 0. So you don't have this term, and all you have is this 1/2 times negative 9.8 times t squared. And then rearrange that to calculate t as 3.19 seconds. And once you get the time, remembering that the horizontal velocity is a constant, you multiply that with the time to get the horizontal displacement. Now in this question, this is a completely different question. You have a 2 kilogram mass and a 3 kilogram mass hanging vertically on an Atwood's machine. This is the Atwood's machine. So you have the 3 kilogram, you have the 2 kilogram. If the masses are released from rest, what is the resulting acceleration of the masses? If you release these two masses, the heavier one, which is 3 kilogram, is going to go down, and the lighter one is going to go up. But they're going to have the same acceleration. So drawing the free body diagram, which is considering only the forces acting on each object individually. First, take a look at mass M1. You have its weight acting vertically down, which is M1G, and you have the tension in the string, which is T. Which one of these two is bigger? Of course, it's T. Why? Because this object is going up. So when you take the net force, you're going to take the bigger force, T minus M1G, is equal to M1A. That's Newton's second law. Net force here is equal to mass times acceleration. Look at the free body diagram for M2. You have its weight, M2G, acting down. You have the tension acting up. Which one of these two forces is bigger? It's M2G. Look at the length of the arrow. It's M2G. Why? Because it's going down. So when you take the net force, it's going to be M2G minus T is equal to M2 times A. Again, Newton's second law. Once you get those two equations, you can solve them. But what I've done is to add the two equations, because I can see that when you add them, the left-hand side has The first equation has t here, second equation has negative t, which means that when you add these two left-hand sides, these two will cancel out because it's plus t and minus t. That leaves us with m2g minus m1g. That's what's written here. And then on the right side, simply add these two. Now on the left side, you see g is a common factor, so take that, and then you have m2 minus m1. On the right side, again, a is a common factor, so take that out, and you have m1 plus m2. We're trying to find acceleration, so divide by m1 plus m2 on both sides, which gives us this equation. And then it's a matter of substituting the numbers carefully. m2 is 3, m1 is 2, and that's there. So denominator, you have 3 plus 2. Do the calculations, you get 1.96 meter per second squared. So that is how you do that. In this question, it's about a car of mass 1000 kilogram taking a curve of radius 50 meter, but there is no banking. So if there is no banking, then the only chance for this car to take the curve is the frictional force. And that's why the coefficient of friction is given here. So when you look at the diagram again, that's the curve. You can see a picture on the left hand side. That's the curve which I've drawn here. And the forces acting are the weight of the car, mg, vertically down, Fn, vertically up. Remember, it's a flat road. You see the road, mg down, Fn up, it's a flat road. So, and then the centripetal force acts towards the center of the circle. If this is the curve, you know that the center would be somewhere here, so somewhere here. So you have the centripetal force. And the centripetal force is nothing but friction in this case. So what is friction? Friction is mu times Fn, isn't it? Therefore, the centripetal force is the frictional force. But Fn is the same as mg. Fn is equal to mg. So substitute here, which gives us mass times velocity squared by r is equal to mu times mg, because Fn is mg. The masses get cancelled, giving us this equation, which you rearrange to take r to the right hand side. Substitute the values. The radius is 50. Coefficient of friction is 0.4 and g is 9.8. And then when you take the square root, you get 14 meter per second. So that's how you do that question. Now, here is a practice problem on the gravitational force. Remember, the gravitational force is a universal force given by this formula. F is equal to G m1 m2 by r squared. G is called the universal gravitational constant. It has this value, it will be given to you. And then if you're given the two masses, it's right there and the distance is here. So to find the gravitational force, just plug the numbers into this equation. So you have 20 and 10, and the distance between them is 10. Remember to square it because the formula is a square. And when you do those calculations, you get 13.34 times 10 to the negative 11 newtons. That is the gravitational force. In this last question, I thought we should try to find the maximum safe speed around a curve of radius 20 meter, but this time the road is banked at an angle of 10 degrees. So we are neglecting friction in this case. Although there will be friction, but just to make it easy, we are neglecting friction. So here is the situation. That's the car. The forces acting on it are mg, vertically down, n, perpendicular to the road. Remember, that's the road. Says the road surface because it's banked. That's the angle of banking. So now you got to break n into its components, which is going to give you n cosine theta and n sine theta. n cosine theta should be equal to mg, and n sine theta is the centripetal force because the center of the circle, center of this curve is somewhere on this side. So that's what I've written. N sine theta is the centripetal force. N sine theta is the centripetal force. And n cosine theta is equal to the weight. With two equations, if you divide the two equations, when you divide the left side by this left side, the n and the n will cancel out. Sine theta by cosine theta is tan theta. And then on the right side, the masses are going to cancel out when you divide, which leaves us with v squared by rg. Substitute the numbers. Tan 10, because it's given us 10 degrees. Tan 10 is equal to v squared by r times g. Tan 10 is this much, 0.1763. Be sure that your calculator is in degrees, and then rearrange that to get v squared, and then take the square root to find the maximum safe speed around this curve, which we get as 5.87 meter per second. And now go through this review several times because it's going to be a very useful one for preparation on the exam. Thank you.